Now our next little piece is a discussion about the confidence levels and the size of the interval based upon the confidence level. Now let us suppose that we have a 95% confidence interval constructed for the population mean. What that indicates is this: we have a 95% confidence interval. Extremely roughly, crudely, approximately speaking, what we say is this: the population mean is a number that falls somewhere between 0 and 1. What we're saying is there's a 95% chance that the population mean is somewhere in here. Again, that's an extremely crude, approximate way to say it, but that's roughly speaking what's happening here. So there's a 95% chance that the population mean is in here somewhere. The population proportion is here. What if we wanted, so we're again, this is very crudely speaking, we're 95% sure that we've covered the population mean using this big of an interval. Now, keeping everything else equal, suppose we wanted to be even more certain than this, keeping everything else equal, keeping everything else the same. What if we want to be 99% sure? We want to be even more confident in our estimate. Well, in order to get more confidence, keeping everything else equal, the only way to be more confident is to cast a wider net. So if this is a 95% interval, then this larger one might be a 99% interval. Sometimes students ask, why don't you just simply make a 100% confidence interval and have 100% certainty? And the reason is this: that can be done. Here's the number line. Here's 0. Here's 1. I want to cast my net. I'm going to estimate population proportion. Estimate the population proportion P. It's on here somewhere. We don't know where. But I want to have 100% certainty that you actually contain the population mean proportion P. Well, that can be done. But think about it. What if I do this? What if I go from 0.001 to 0.999 and I take that much as my confidence interval? Are we, even theoretically, are we 100% certain that there's no way in the world that the population proportion could be out here? Well, no. Theoretically, we could have an extremely bizarre setting, and even though we're going from 0.001 to 0.999, we're not 100% certain this is going to work, because it could be the proportion value falls either here or here. In order to be 100% certain, you need to say all the way from 0 to 1. Now, that is a 100% confidence interval. The probability that you have not captured this population proportion is 0. This is guaranteed to work. The problem is this doesn't give you any information. Nothing useful. It doesn't do any good to go to the boss and say, I am 100% certain that I know what proportion of voters are in favor of this ballot initiative. The boss says, wonderful, what's your estimate? Well, I'm sure that somewhere between 0% and 100% of the voters are in favor. Well, we knew that going in. In order to have a useful piece of information, you must pare this down so that now you can have a meaningful piece of information. The instant you do that, you allow for at least the possibility that there is some error. And so it's this balancing act between something that is reasonably useful and yet not so fraught with error. So one extreme would be to cast the net so wide that you catch everything, which means there's no information of valid use. The other end of the spectrum would be this. I'm trying to estimate the proportion of voters. Suppose we say it's 44% or 0.44, but suppose our margin of error is 0.000001. Our margin of error is tiny. Now, is there a possibility that the population value falls out here? Well, yeah, there's a really good chance. This is an extremely tight estimate, but the probability of this being correct is going to be very small. So as this gets larger and larger, the probability of being accurate increases. But if it gets too large, as we had up here, then it becomes, for a practical purposes, useless. That balancing act is what we're going to be on about. And vast experience has shown that typically 90%, 95%, or 99% are the three most widely used values. And of those three, 95% is far and away the most widely used. The 95% is the most widely used at the basic level of study. Now, as you go into more detail work and more sophisticated expressions, that changes. But at the basic level of study, 95% is the most common standard. These three are most common, and even of those three, 95% is the most common. So, if a 90% confidence interval looks like this, suppose this is 90%, the question is, keeping everything else the same, would a 95% confidence interval, would it be wider or would it be more narrow? Well, the way to think of it is this. In order to get 100%, you go out all the way. And as you come in, this value gets smaller. So 100%, 99%, 95%, 90%, 85%, and so on. So if this is 90%, 95% is going to be larger. 99% is larger still. If someone wanted to compute an 80% confidence interval, it would be smaller. You could, if you wanted to, construct a 10% confidence interval. And if you did, it would be a very small number. The margin of error would be very small. But the problem is that you have only a 10% chance of it being accurate. Again, roughly speaking. So that's the relationship between the length of the sample size and the confidence level.